So, a minute ago I gave you the simplest demonstration of just a spherical micelle that forms for aggregating insoluble chains in the center, surrounded by the swollen cell, the shell. When you make these, if you were to play with the different lengths of the two chains that you attach together, you can go from a very short insoluble chain relative to the soluble chain, and all the way vice versa with a very short soluble chain and a large amount of water insoluble chain. And by playing with these different things, you're going to change the curvature that's induced, represented by the cone, in the structures that form. And so by playing with the two volume fractions of each block, you can then drive different shapes that form in solution, going from small spherical micelles to long cylinders, which can be quite short really in the real world, but quite long in terms of the scale of these. And eventually you'll get sort of a bilayer in terms where you have two polymer chains coming back together and forming this enclosed membrane. They would ideally like to form very long extended planar layers, but you see you don't want this. It doesn't like a bare end in solution, so the sheets actually, when they form, curve around, and you end up with sort of a soccer ball shape with filled with water in the core. And these can be useful. So if you had, say, a drug that was not soluble in water, but you wanted it to be soluble in water, you can add these polymers to the solution of your drug, and encase the drug in the core of these, in effect solubilizing the drug so it can be carried throughout in the water system. With the vesicle as well as encapsulating insoluble compounds within the membrane of the vesicle, you can also encapsulate compounds that are soluble in water anyway, but perhaps if the environment you're going to put them in would degrade them and break the compound down, you can trap them inside the vesicle, protecting them from the outside until you get to where they want them to be. So that is found in everyday uses. So spherical micelle is what you use every day to wash your hands, wash your clothes, and you mix it up in the water, you throw your soap in, and any dirt on your hands or oil and grease, ketchup, or spilt down your shirt is going to be trapped. It's going to move into the core of this micelle, because that's where it prefers to be. So then you rinse away the soap from the solution, and this takes away all the dirt, and you're left with clean hands, clean clothes every day. So these cylindrical micelles are very similar to structures found in nature, such as this is the Ebola virus. This is a picture taken on a microscope of those. So this is a way we can mimic this shape. And by looking at how this reacts in your solution, it's like a model system for your virus, which is a much more complicated system to try and look at. And then the vesicle, which is a big bilayer encompassing a water-filled core, is analogous to say the membrane of a cell, which is used to entrap everything. And the cell is incredibly complicated. So it's got this big membrane which traps smaller membranes within inside it, so that everything happens there. So see, this would be an incredibly complicated system to look at overall, but so this can be modelled with the vesicle as well. This is just a micrograph taken of a slice through a cell as an example. And this is a picture my colleague took at Sheffield, and this is an actual vesicle forming off a surface here. in the water solution. So they've made a thin film of the polymer, added water, and the polymer swells up, forming these vesicles in solution. This one was in fact labelled with a dye so that it would fluoresce when you looked at it under the microscope. It's the glowing red colour. So a lot of my work at Sheffield was involving vesicles of this kind, and then towards the end I'll move on back to the micelles that we saw. Taking these vesicles as they are, you have in your sample a whole dispersion of thousands, many vesicles in solution, and they'll remain there stable